You were muted, but I could hear you from next door. So, all right. Well, I want to welcome everybody to the Meadows Center Blue Bag. We call it a blue bag because we're generally focused on water, but folks can enjoy their lunches. I think one thing we learned during the pandemic was it was easier for people to attend via Zoom, and so here on out we're planning on doing these on Zoom. We've got some folks from other parts of the state and across campus. So we'll continue to do that as we go forward. Happy to introduce today's speaker, Dr. Soe Myint. He's the Meadows Endowed Chair and Professor at the Department of Geography and Environmental Studies at Texas State University. He also serves as the Chief Conservation Officer here at the Meadows Center, and he's been with the university pretty brand spanking new since January, and very happy to have him. As far as his pedigree, he's got a bachelor's of science in forestry from Rangoon University, master's of science in the natural resources program from the Asian Institute of Technology, and a PhD in geography, geoscience from Louisiana State University. We'll hear some about his research interests with his presentation today, but his stated research interests: remote sensing, geospatial technology, environmental issues, water use and management, landscape ecology, and ecosystem services. I was taking a peek at Dr. Myint's CV and notice he's got a paper in press that I think encapsulates some of his research interests. I'll just read you the title: An Innovative Scheme to Confront the Trade-off Between Water Conservation and Heat Alleviation with Environmental Justice for Urban Sustainability. Dr. Myint has received many awards and honors and has published many papers. So, Dr. Myint, I'm so happy to have you at the university with the department and working with the Meadows Center, and I will turn it over to you.
Thank you so much, Robert. That's very kind of you. First of all, thank you all for joining my research talk. I would like to explain a little bit about my PowerPoint presentation. Since I have been here for like only 1.5 months at Texas State University, so this talk is like introducing myself to you all, and also sharing my research activities, as well as to demonstrate how remotely sensed data or technology can be used to monitor or evaluate the water-related issues and come up with some kind of solutions or formulate policies and then modifying rules and regulations, things like that. So I'll try my best to cover many different areas. So bear with me. I'm planning to cover like 7 different research projects, but it has been suggested that I should go for half an hour, followed by questions and answers. So you can imagine 7 projects in half an hour. It will be like a bullet train, or it will be like a lightning talk or elevator talk. You have to finish everything once the elevator stops at the 7th floor or something to cover your research. It will be just like that. So I would like to apologize before I give my presentation. Please bear with me. I will move really quick to cover as many as possible. So there are 7 different projects. I'm going to share the screen now. Somebody tell me, can you see the my PowerPoint slide?
Yes, we can.
That's okay, great, thank you. So I give the title Remotely Sensed Water Issues and Solutions, not really maybe solutions, but to formulate new policies or modify the existing policies, or come up with better management options or things like that. So I'm going to give like 7 examples. So the first one is examining the ecosystem health and sustainability of a coastal environment. The second item covers ground and surface water changes. The third study deals with urban heat and water issues. And the fourth is social inequity and environmental justice. The fifth is water use and drought in lower Mekong Basin. And then sixth is agriculture versus water conservation. And the last one is the one that Robert mentioned, spatial optimization model to confront the trade-off between water conservation and heat alleviation. So the first one, examining the ecosystem health and sustainability. So the background is that mangrove forest has been declining, rapidly declining across globe. And then, we understand the valuable services. It is even basically, we call it like carbon sequestration, absorbing the carbon. That is basically called blue carbon for mangroves. This is the biggest value of mangroves ecosystem service. And the study area is actually Sundarbans Forest, which is the world's largest forest spanning the border between Bangladesh and India. And so this is the example of some images of mangroves. And here is the study area. You can see the red line, the left part of the Sundarbans forest belongs to India. The right one is Bangladesh. And I use percent tree cover and enhanced vegetation index and annual net primary productivity, leaf area index, evapotranspiration, which I use as a consumptive water use. So this percent tree cover, net primary productivity, evapotranspiration images are available annually. And then we basically computed mean EVI, enhanced vegetation index and leaf area index, and then taking average for all of them for the same year. We created 5 layer stacks, basically from 2000 to 2010 of percent tree cover, enhanced vegetation index, net primary productivity, leaf area index, and evapotranspiration. And we perform pixel-based time series analysis trend of these changes in the past 10 years, 11 years, using OLS regression. This is the output of percent tree cover. You can see red color pixels and orange color and yellow color pixels. That basically shows the percent tree cover is declining in those areas. Those red pixels, orange and yellow color pixels are on the east side of the study area. Most of them are in Bangladesh, part of the world's largest mangroves, Sundarbans forest. And leaf area index, again, red, yellow, those pixels are in Bangladesh side of the Sundarbans forest. And enhanced vegetation index, again, yellow and orange pixels on the east side of the study. And carbon content, change of carbon content, basically releasing carbon into the atmosphere, red pixels, again, orange pixel, yellow pixels on east side of the study. Evapotranspiration is also declining in most of the areas in Bangladesh side of the Sundarbans forest. So let me give a conclusion. The Sundarbans forest in Bangladesh side is basically experiencing annual forest degradation rate of 2.2%, but the Sundarbans forest in Indian side of the area is only 1.64%. So basically, we demonstrated that the Sundarban was encountering fragmented degradation within the forest, even though it is basically claimed as well-managed, well-conserved forest. It is being watched by many international and UN organizations, including World Bank, Asian Development Bank, United Nations Environment Program, FAO, and UNESCO, and so on. All of them are watching the world's largest mangroves, and they believe it is well managed, but we demonstrated that there are some kind of deforestation and degradation going on. Even though degradation seems to be low, but in some area within the compartments, some compartments, parcels shows really high degradation. We came to know that there are some kind of shrimp farms and fish farms activities going on within the forest. And the carbon release is that 5,608 megagrams carbon was lost in Bangladesh side of the Sundarbans forest. So mean annual water, consumptive water use loss rate in Bangladesh side is 8.56 millimeter per year, whereas Indian side is 6.09. So in general, Indian side of the Sundarbans forest was managed better than Bangladesh side of the same forest. So here, the second item is examining ground and surface water changes in response to environmental issues and land use dynamics. So this is part of my Fulbright Canada Research Chair in Water, Environment, and Clean Energy. I went to Canada and conduct this research. So overall goal is to see whether there is changes in surface and groundwater in Canada between 2002 and 2017. We would like to know whether there is some kind of biophysical, socioeconomic, and land use land cover dynamics that influence these changes. The study area is actually all the provinces in Canada. At first, we were thinking of taking only on the southern side of the country. So it's like British Columbia, Alberta, Saskatchewan, Manitoba, Ontario, Quebec, New Brunswick, Nova Scotia, Prince Edward, Newfoundland, and so on. So we use gravity recovery climate experience, GRACE data, to see the changes. We also use net primary productivity layer, percent cover layer, annual evapotranspiration layer, land surface temperature layer, and enhanced vegetation layer, leaf area index layer, all of them. And here is the brief overview of GRACE data. Delta TWS is the pixel value. Delta TWS is the total water storage in each and every pixel. And delta SMS is soil moisture. Delta SNO is snow cover. If we have total soil moisture and if we have snow cover, if we subtract these two, we will get ground and surface water. But if we have surface water layer, then subtracting these three would lead to groundwater changes. But in my case, we didn't get surface water layer. And so we basically check ground and surface water changes together. The baseline for the mean data is between 2004 and 2009. Take the average and subtract it so that which year, which value is getting higher than that average data. So instead of presenting all layers, I'm just presenting that water expansion rate and water expansion by area. And deforestation rate, British Columbia is the highest, followed by Alberta. And forest degradation, again, British Columbia, in terms of degradation, Quebec was the second highest. And agriculture changes, Manitoba and Ontario basically experienced agriculture decline in agriculture area. The highest is Nova Scotia. So here is the results of, let me change this, I couldn't see the title. Results of enhanced vegetation index. That is the trend of that enhanced vegetation in the past 20 years, 17 years. This is also the trend of leaf area index from 2002 to 2017. The trend of normalized difference vegetation index gain from 2002 to 2017. Trend of land surface temperature for those years, and then trend of ground and surface water changes over these years. So I'm going to present now the increasing trend of water in the GRACE data. This is Quebec. You can see the upward trend. That means the ground and surface water changes basically shows increasing trend of ground and surface water. And this is New Brunswick. You can see somewhat, it is not as steep as the above diagram for Quebec, but it is somewhat flat. And this one is for Ontario, But if you look closely, you can see that there is a decline trend after 2011 for Quebec and Ontario, sorry. And this one is Nova Scotia, which is also somewhat increasing trend. These provinces shows a stable trend. For example, Newfoundland, this is somewhat straight line, no increasing, no decreasing. But if you look at it carefully, after 2011, there is a decline for Newfoundland. And this one is somewhat straight for Prince Edward Island. And this is Alberta. Again, there is a decline after 2011. And provinces with decreasing trend of water. In general, these basically give a negative slope over the entire time periods, getting lower and lower. And you can see, again, this province also show after 2011, there is a decline. And this is British Columbia, declining trend over the entire period, but it is still showing a steep slope after 2011. And then this is Manitoba, again, the same trend after 2011. And then we did all provinces and then the entire study area together. You can see all vegetation indices positively correlated. Net primary productivity is also positive. Whenever net primary productivity is high, the water storage is also high. And whenever it is low, net primary productivity is low, the water storage is low, leaf area index is also the same. Land surface temperature is negatively correlated, meaning that warmer areas, hotter climates basically face the decline in water. And the other one is deforestation, which is also negatively correlated. Let me switch to conclusion. All vegetation index indices and percent tree cover are positively correlated. Whenever they are high, ground and surface water gets higher. Land surface temperatures are negatively correlated, warmer areas, and then lower ground and surface water. Deforestation rate is negatively correlated. So whenever there are deforested areas, you will see ground and surface water decline. And see those provinces, 3 provinces shows the trends of stable trends, but all other provinces either negative trend, or even though if it is not negative, you will see the decline, sharp decline after 2011. And so that's basically the finding. And let's move on to the next one, formulating operational mitigation options and examining the urban social inequity, which is part of my NASA EcoStress funded project. I serve as the PI. And research objectives, the goal is to evaluate environmental inequity of heat and drought exposure, as well as water use, which is basically outdoor water use among different socioeconomic status and racial ethnic categories. So we basically investigate the relationship between that EcoStress, NASA EcoStress land surface temperature, evapotranspiration layer, evaporative stress index, and then link with all these demographic, socioeconomic factors. So here is the study area of Phoenix. You see a lot of man-made features in the desert environment. And socioeconomic indicators, household property values, median household income, percentage of household below poverty level, and EcoStress data, land surface temperature, evapotranspiration, which is proxy to consumptive water use, and evaporative stress index, which is sort of like a drought indicator. And we use all these 3. With regards to race and ethnicity, we use all race and ethnicity, white, African American, American Indian, Asian, Native American, 2 or more races, and diversity index. Here's an example of land surface temperatures, and then I'll jump on directly onto the results. You can see the vegetation, race, and ethnicity. We got different kinds of relationship. Let me just pick the first column, Hispanic, negatively correlated with vegetation index for both summer and winter. That means the higher the Hispanic population, the lower the green vegetation biomass, the lower the trees, grass, and shrubs. And then golf course is positively correlated. Normally, golf courses are a little bit outskirts of the city, not inside the urban core area, so which is positively correlated. Maybe we don't know exactly, but for the parks, it is negative. The higher the number of Hispanic, the lower the percentage of parks, which is basically sort of like environmental inequity or social inequity. Here is the water use and evaporative stress or drought. Again, let me pick Hispanic alone. And so Hispanic is negatively correlated to drought index, or I would call drought index, which is basically evaporative stress index. Negative relationship means the higher the number of Hispanic population, the higher the drought condition, because the lower ESI, lower evaporative stress index, means high drought condition. And this is true for both summer and winter. And then it is also like negatively correlated to total evapotranspiration, which is like proxy to water use or moisture around their areas. So the higher the number of Hispanic, the lower the water use, consumptive water use, or the lower the moisture around their area. So here is the trend of environmental factors between 2000 and 2020. Again, the LST is positively correlated. The higher the Hispanic population, the lower the trend of slope of LST. I'm sorry, positive. So the higher the number of Hispanic, the higher the land surface temperature slope. And air pollution is also positive. The higher the number of Hispanic, the higher the rate of change of aerosol optical depth, which is air pollution. And then the negative trend for NDVI, which is the higher the Hispanic, the higher the lower the vegetation cover. And the same thing, the higher the Hispanic, the lower the slope of evapotranspiration or water use. So the conclusion, household property values, median household income has negative relationship, suggesting that people with lower income experience higher urban heat. American Indian, Alaska Native, African American, Hispanic, positive correlation with LST. They live in warmer areas. Hispanic, Black, African American, Native American, and other races, diversity, all of them are negatively correlated to drought-prone areas, which is all statistically significant. And it is true for water use, outdoor water use. It also shows same patterns like drought. All these things, same race and ethnicities experience higher drought conditions. Okay, so this is another one, widespread race and ethnicity disparities with respect to social and environmental inequity issues. This is also NASA-funded project. And we examine the widespread disparities of multi-directional, this time for larger area coverage for many different states, evaluate the impact of climate change on environmental inequities in the past 20 years. This is the study area. You can see the states. It also covers Texas. And as far as I remember, at least Dallas and Houston is part of the study. Let's move on to the next one, eco-stress data, land surface temperature, and evapotranspiration, consumptive water use, and evaporative stress index, that is drought. Let me just pick only one category, which is African American. African American is negatively correlated to median household income, negatively correlated to per capita income, positively correlated to percent household below poverty level, and median housing property value that is negatively correlated. So daytime land surface temperatures are positively, there is no relationship, but evaporative stress drought is positively correlated. And water use is also positively correlated, and land surface temperature trend is negative, evapotranspiration outdoor water use is negative. Again, we try to see what is the difference in the weighted mean among Hispanic versus non-Hispanic, and people of color versus non-Hispanic white. Let me just pick only one column. You see the negative relationship for median household income and per capita income, negative for housing property value, minus 77.30, and evapotranspiration water use is also negative. Evaporative stress index is also negative. Land surface temperatures are positive with the land surface temperature slope higher the Hispanic in comparison to non-Hispanic positive. And water use negative, the higher the Hispanic, less water use, less moisture, less humidity. And then we also basically take the mean value. You can see land surface temperatures are somewhat positive going up, and evapotranspiration of those two at the bottom, somewhat negative. Let me show you a little bit more into detail. Those figures on the left is for arid, semi-arid, or desert condition. And the right ones are temperate. The first one is Hispanic versus non-Hispanic. The second one is people of color versus non-Hispanic white. In arid desert conditions, environment, all of them are positively correlated. You can see temperate part, water use or consumptive water use or moisture outside the environment is basically showing the negative trend over time. Let me move on. We also basically try everything total plus one for arid, one for temperate. We basically use the LST differences. In general, top two are showing somewhat positive, and the bottom two are negative. We basically subtract Hispanic temperatures at each pixel minus non-Hispanic temperature, and do the same thing for temperature in people of color minus the temperature in non-Hispanic white, and show some positive and negative trends. And let's move on to the next one, consumptive water use variation across biomes in the lower Mekong Basin. This one is basically connected to my NSF Infuse project. I served as co-PI. We basically selected Mekong River, which is one of the world's largest and most biodiverse rivers. It basically covers China, Burma, Laos, Thailand, Cambodia, and Vietnam, from the headwaters to Tibet to the sea. But this lower Mekong River basin cover Burma, Laos, Thailand, Cambodia, and Vietnam. So we try to map the annual consumptive water use. We evaluate the water use variation among different crop types and different biomes, examine the land cover type specific water use variation with regards to climate zones and elevation. So here is the study area for those 5 countries. And we basically process those gap filling techniques and then processing individual layers, interpolated to get 365 layers for the whole year to get the annual water use. Here is annual evapotranspiration. The one in the middle is agricultural types. The one on the other end is biomes and cover types. This is the validation of evapotranspiration and water used by crop types. You can see irrigated crop and irrigated rice in general consume more water, but in some cases, orchards water use is a lot more. It depends on what type of orchards in which countries. Basically, it depends on the situation. Water used by forest types in general, broadleaf evergreen and broadleaf deciduous, basically are the 2 categories that are using a lot of water, or the highest level of water. In some cases, shrubland also use a lot of water. Shrubland could also be part of orchards as well, or some kind of rubber plantation or palm trees plantation and so on. So regression analysis results showing the relationship between water use and elevation. You can see either agriculture types or biomes of different forests. Our square values are all positive. All of them are statistically significant. They all depend on elevation. The water use depends on elevation. Water use variation among climate zones, which is basically is an ANOVA test that the result basically indicates the annual ET that is basically significantly different among at least one pair of agricultural types, climate zones, and their combined effects between agricultural types and climate zones on annual water use. Here is water use efficiency for the entire Mekong regions for 5 countries. And here is another ANOVA test. Basically, it shows water use efficiency is significantly different at different NDVI levels. We just wanted to show different NDVI. If we show everything together, people may argue that the higher the NDVI level, it is supposed to be more water use efficiency. So we split it and then show it's still significant. This is each biome types for each diagrams and showing NDVI levels. Normally, high NDVI supposed to be more water use efficiency, but it is not completely true in some climate zones. Some moderately high are even higher, or medium is higher. So this one is NOAA funded project. I serve as the PI, adapting crop water management under climate uncertainty and spatial decision support system. So this one, research question is how agriculture water use responds to drought conditions, which crop types are vulnerable to drought in terms of water use, and what adaptive options can be applied to solve this issue. So here is the Phoenix active management area. And here the crop type mapping, we interviewed USDA Farm Services irrigation district managers, took fieldwork interview with local growers, and using remote sensing machine learning algorithm. And this is example image. This is the output map. We basically prepare crop type maps for 2 drought years and 2 wet years. Here is the validation of evapotranspiration that we generated using Landsat-TM image. And here's another validation at the farm unit level or each irrigation district level. So you see the water use, mean water use for each crop type in dry year is higher than wet years, except cotton, which is not really the case. That argue when I organize 2 workshops and invite all USDA or irrigation districts managers and Agribusiness Council and Water of Arizona and Arizona Department of Water Resources, but mainly local farmers do not believe that crop water use in dry years and wet years are not different. They use the same amount of water. This is the result that we got. And again, we did the ANOVA test, regardless of which crop type or which irrigation districts or which year, either drought or wet years, they all are statistically significant. And I'm just showing some example. If we extract alfalfa alone, we use 2.639 billion gallons more in a dry year. Same level of water use, regardless of which year, is not really correct. And again, another one really quick, I'll just extract only alfalfa and cotton. 56.81% of the water goes to alfalfa. This is desert environment. And alfalfa is the most water use crop. And that is the biggest. 25.36% of agricultural water use goes to cotton. 51 billion gallons of water used for alfalfa. 22 billion gallons used for cotton. And a dry year, we use 2.6 billion more gallons for alfalfa. In dry years, we use 479 million more gallons used for barley, and we use 388 million more gallons for corn. And to know that barley is the biggest water user in the dry year, which is followed by wheat, alfalfa, wheat, sorghum, and corn. And we also tested what if we plant 2 crops at the same time. If we grow barley and cotton together, we could have saved 9.749 billion gallons in a year, or 22.87% of water use. And given the same condition, barley production could have been 9 times higher, and cotton production could have been 12.51% higher over the original crop yields. So the conclusion is crop use more water in dry year, Water use varies by irrigation districts. Alfalfa use the highest amount of water. Cotton is the only crop type that uses more water in a wet year. And double crop uses less water. Crop production is potentially high given the same biophysical and water conditions. Consideration of drought-tolerant crop types is crucial. Disproportionately large areas of high water consumption crops needs to be reduced or replaced with other more water-efficient crops that can even make better profits, better income. And reduction of total crop area, acreage, or water use, reduction of water use, like the way California is practicing, may not be necessary if we lower water use crop types, drought-tolerant crops, or introduce double or multiple cropping practices. So that's basically the one. This one is an innovative scheme to, I'm going a little bit more than what I'm supposed to do. I'm sorry for that. This is the last one that Robert mentioned, recently published in AGU Advances, an innovative scheme to confront the trade-off between water conservation and heat alleviation. NASA funded project. I serve as a PI. Research goal is to basically tackle the trade-off between water consumption and heat mitigation. In order to mitigate heat, we need to increase green infrastructure. When we increase green infrastructure, we use more water. More water conservation is the key, not only in Arizona, it is true for the entire country. So here are the data that I use. That US Census block, a block level for socioeconomic data, and environmental databases for land surface temperature, evapotranspiration, and then also those for Landsat-based summer LST changes and summer ETA changes. Here we use the 3 segments to identify areas, basically identification of required areas. Priority area is the first one, basically the population above 25th percentile, median household income below 50th percentile, blocks of property values below 50th percentile. When we help those economically stressed neighborhoods and areas with high population, we try to mitigate heat and air pollution by increasing green infrastructure. We also help the entire city, not only them. The entire city temperatures will go down. Water use will also go down, kind of like that. So hotspots, we basically use a daytime land surface temperature, 50th percentile, and LST during the winter, and LST during the summertime, nighttime and daytime, I'm sorry. And then blocks of summer for evapotranspiration, water use, and drought layer of that hotspots. Take all these things, that's the environmentally stressed areas. Then opportunity areas, we use 20 years of land surface temperature and evapotranspiration changes. Areas of pixels that experience lower land surface temperature over time or higher water use and evapotranspiration over time are considered opportunity areas for saving water. And so this is the map of soil, trees, grass, and shrubs that we use. And here's summer LST to take the mean, and you get the summer LST mean. And that one was the previous one of daytime. This is the nighttime land surface temperature means. This is summer evapotranspiration, and basically for 92 days, I'm interpolating for all 92 layers and add up everything. This is the whole year's summer water use. And this is basically drought evaporative stress index, which is a drought kind of indices. And then we take the mean instead of interpolating the actual stress and drought in the summertime. This is for land surface temperature. And then we basically take 2000, 2001, 2002, 2003, all the way to 2020, and take all of them and layer stack onto each other using man-candle tests to show which area is experiencing increasing land surface temperatures, which pixels are experiencing decreasing land surface temperature. We did the same thing for water use for 2000 ET, 2001 ET, and all these things for up to 2020 and layer stack all of them for water use in which pixels is getting higher and higher, which pixels are experiencing lower and lower between 2000 and 2020. And here are the output for nighttime land surface temperature, outdoor water use, and drought conditions. All of them, we basically take 25th percentile interval. And here are the output of priority areas, residential districts, socioeconomically disadvantaged neighborhoods, lower per capita income, lower housing values, hotspot regions, higher temperatures, higher drought-prone areas, higher lower water use areas, and opportunity areas of increasing trend of evapotranspiration and decreasing trend of land surface temperature. And this is the optimization approach. And I'm almost done, I'm sorry. We basically try to maximize the LSD reduction and minimize the outdoor water use increase. Outdoor water use increase will be minimized, and LSD reduction will be maximized using all the information that I talk about, plug into optimization, and we got this basically output where to grow what types, whether trees or grass or shrubs, but we can switch the weight to basically determine which areas needs more or which areas needs some kind of serious attention and so on. I think that's pretty much the last one. Well, thank you all so much for being patient and bear with me.
Very good. Everybody hit your clap button on the reactions.
Thank you.
or snap.
Thank you.
The cheers are deafening. Welcome to put the questions questions in chat, or go ahead and raise your hand.
Okay.
No questions?
Tired of my long talk with lots of activities.
Everybody must have had a good lunch. They've got a carb dose going or something. All right, go. Here we go. Trey has a question.
Good afternoon. Thank you so very much for that presentation, and certainly the temporal and the multifaceted approach to evaluating the pixels is really interesting. I have a two-part question. The first would be, what's the smallest subset from the various satellites that relates to land acreage in general on the ground that would be representative year over year, right? And then secondly is really, have you correlated that between some of the other popular drought indices or long-term cumulative variance to precipitation in the periods before and after some of the trend data, just to see if years immediately before the study period had a drastic effect or a leading indicator effect going into your study? Please and thank you.
Yeah, could you please repeat the first one? I missed it because there is some kind of cuts and.
Well, the first one is, it's really exciting taking the satellite, the remote sensing, and looking at pixel versus pixel. What's the best resolution? How the smallest area you can definitively identify pixel for pixel year over year?
Okay. Yeah, the first question, we use most of the spatial temporal layers that we layer stack is all Landsat based, so which is like 30-meter resolution Landsat. We generated evapotranspiration layer using Landsat 30-meter resolution. So that evapotranspiration layers, we basically, there may be 19 Landsat images for the whole year of the study area. We basically interpolate those 19 layers using additional coarse resolution satellite images to generate 365 layers of evapotranspiration or 365 layers of land surface temperature, and basically layer stack all of them to perform space-time analysis, as you mentioned, spatial temporal analysis. Another one is recent eco-stress data that we use is basically about 70-meter resolution, which is basically, again, evaporative stress index, water use efficiency, and also evapotranspiration. Most of the areas, I'm sorry, I didn't get a chance to talk. The biggest one that we use basically is MODIS net primary productivity carbon content, and MODIS enhanced vegetation index or normalized difference vegetation index or land surface temperature, evapotranspiration, all of them are 250 meters to 500 meters for the entire country of Canada, which is a little bit coarser resolution. Again, so in different case studies, different research, there are 250 meters to 500 meters resolution for regional large area analysis. And most of the time, we use Landsat-based air pollution that we generated, or Landsat-based evapotranspiration that we generated, or Landsat-based land surface temperature to get the entire area. That is 30-meter resolution. EcoStress is 70 meters, but it is used. I didn't get a time to say exactly what are the resolutions. So in general, 30-meter resolution of changes that took place. Let's say if we are interested in observing something in Austin or San Antonio, we will get the entire San Antonio city at 30 meter. Every 30 meter have land surface temperature changes or outdoor water use changes or drought condition changes or air pollution changes that we can determine and then link with water use to determine how to mitigate air pollution and heat by increasing green infrastructures. And I forgot the second question.
No, thank you. No, that's excellent. I presumed it would be different resolutions, but I was hoping to kind of understand that when looking at some of the compiled graphs. The second one, I guess, is something that I know that in talks I've had with Dr. Mace, looking at the longer term trend, when you analyze for a 5-year or 10-year study period, what additional validation are you looking at as far as time period before and after to long-term drought or, you know, positive surplus of normal rainfall versus negative variance to rainfall before and after that might affect your slopes during those years? I'm just curious how you, as the PI, how you approach that time period before and after.
Yeah, that's an excellent question. You know, there is some kind of variation in each year, like, you know, extreme drought years or in general, all drought years, maybe, you know, surface temperatures are high or air pollution is high or evaporative stress index or, you know, things like that are high, regardless of winter or summer or daytime or nighttime. But it would be a good idea to split into drought and wet years separately, or for one particular year, if we would like to explore the trend of changes, which is drought, and we could basically segment one particular time period at a time, how much rainfall intensity or frequency happened 1 or 2 weeks before this particular satellite image is taken. And then that would be, like you suggested, that the effect from the previous 2 weeks have a huge impact on that particular satellite image that shows land surface temperature or vegetation index or evaporative stress index. And so it could have helped for if we go for, you know, annual kind of evaluation. What if drought is exceptionally high, last 6 weeks, no rain at all? And then what is the consequences of this happening in that particular satellite image acquired right after that two weeks of drought? We can still explore that options. That is true for, you know, all satellite image. It could have been air pollution as well, I would say, evapotranspiration or water use, or, you know, after 1 week of heavy rain, annuals and perennials will pop up. And if we take NDVI or enhanced vegetation index, leaf area coverage, these things will basically, you know, pop up. And so the green up areas will be basically increased because of that 2-3 weeks of heavy rain. Rain intensity is high, frequency is high. Then we got really high green up than the satellite images. That may also lower land surface temperature and air pollution, plus having really bump in water use as well.
So I try to try to end these presentations about 10 till to give people
Okay.
time to get ready for the rest of their afternoon. So thanks again, Dr. Myint.
Great.
There is a question for you in the chat, so I'd encourage you to take a look at that. We'll keep the meeting open. It's a question from Yipeng that you could respond to him later on, but you can also contact Dr. Myint via email. His contact information is online. So thanks everybody for attending. Thank you again, Dr. Myint, for a fascinating presentation. And hopefully we can get some some collaborations going on and leveraging your knowledge and expertise. So everybody have a good rest of the week.
Thank you all for joining. Have a great weekend.
Thank you.
Bye-bye.